There we go. Now I got sound. What a way to start a new year off, right? So welcome everybody to another IAEI News Live. My name is Thomas Dimitrovich. And today is Tuesday, January 2nd. Unbelievable, but it's true. We're back in the saddle in 2024. I can't believe, it seems like, it's hard to believe that I haven't streamed since last year, you guys and gals. So, welcome to 2024. Happy New Year. Today, I thought I would cover, I'm going to talk about 30 kVA transformer today, I think it is. Yeah. So I think today is a 30 kVA transformer day, and hopefully we can pull some stuff together. We'll take the journey through picking your overcurrent protective devices, and so I think we should just get started. Today, IAEI News Live, we're going to talk about and learn about 30 kVA transformer. And it all starts now. All right, welcome back. So let's talk about the 30 kVA transformer. Are we out there in the world? We got a lot to cover. So anyway, hopefully hey David, thanks for joining in, and Happy New Year to you, sir. So hopefully you can, hopefully you had a good New Year, you had a good Christmas, all that jazz. It's hard to get back into the groove of things. I don't know about you. I'm just having a time here trying to get back in gear. I mean, geez, oh man. Michael Hofken, Happy New Year. Happy New Year. So I am up in I'm up in the office today. Jake is getting better. So 2023, again, 2023 for Jake was a rough year. He had surgery on his ACL. He is recuperating from that. We don't go until the end of the month to get x-rays out at Ohio State. I get back from Code Panel 2 meetings, and we go straight out to Ohio State to get his x-rays, and hopefully he's healed up. But Michael, I wanted to cover what do you call it? Close some stuff here. I want to cover 30 kVA transformer, and I'll tell you what. We did a 75 kVA transformer on this channel, and we also did a 75 kVA transformer, and I think we did a 112.5 kVA transformer. And I thought, let's I get questions about 30 kVA, and I'm still getting questions. I am still, believe it or not, getting questions about using the 6 disconnect rule on the secondary of a transformer. I still get those questions, and I want to cover a little bit of the journey through the code book in regard to what you can and can't do. Now, I'm going to use the 2023 edition of the book. Hey, Happy New Year, Nihad. And you were into the new year a lot sooner than I was, because you're, I think, 6 or 7 hours ahead over there in Egypt. So, I don't know. So in any case, I'm going to use the 2023 code book, but keep in mind that it really doesn't, in my opinion, I don't believe the sections have changed. I know the fundamentals have not changed. Have the section numbers changed? I really don't think so. All of the sections that we're going to cover today and in our journey is going to be pretty consistent going back in time in the code book. So grab any edition of the code book, whichever that you're in. Yeah, this is the first live stream in 2024. I'll tell you what, and it started off rough. My microphone, I forgot to press the on the microphone. I started my software and my my camera didn't work. I just realized I'm not powering my phone, so hopefully it doesn't die halfway through here, and we don't have video. But you'll know that when it happens, or if it happens. But we had a rough start, Nihad, rough start. So in any case, I'm going to be working in Article 450 for transformers. We're going to look at Article 240 when we start talking about transformer secondary conductors, not tap conductors, because in our case today, and maybe that's something I should do. Let's set up our assumptions. Well, let's do this. What is the first thing that we need? Well, I'll tell you, I'm going to try something here, and yeah, it worked. Good. So let's talk about our parameters, right? So what are our parameters? One, we need to know the kVA. And we know this is a 30 kVA transformer, piece of cake. Number two, we need to know our voltages. And we're going to say primary is 480. We're going to say secondary is 208, 120. Okay? We're going to need to know configuration. I'll call it configuration. And we know we're going to have a delta to Y ground. That's important. And why is that important? That parameter, that little bit of information tells us that these transformer secondary conductors are not tap conductors. Okay, so secondary conductors not equal to taps. Why is that the case? Why is that the case? Let's do this. How do we know this? We're going to go to Article 100, and we're going to look at what is the definition of a tap conductor. Now the question is it T for tap or F for feeder tap? I'm going to go, I just passed up the F's, and I'm going straight to the T's because I think my gut is telling me it's going to be T for tap. And am I right? Yes, I am. Tap conductor. All right. This is the definition of a tap conductor. A conductor other than a service conductor that has overcurrent protection ahead of its point of supply that exceeds the value permitted for similar conductors that are protected as described elsewhere in 240.4. All right, so let's do this. I'm going to draw out our so I have, this is breaker 1. This is breaker 2. This is conductor 1. No, conductor 2. And this is conductor 1. Now, on the primary side, right, so this is, we said this is 30 kVA. We said it was 480, 208, 120. We didn't say the transformer impedance. Let's, I don't know, let's use 4%. 4% Z, and I just made that up. So, all I have to say about that. So now this conductor on the secondary, if I look at the definition of a tap conductor, a conductor other than a service conductor that has overcurrent protection ahead of its point of supply. All right, so now in this case, this is delta Y ground. There is overcurrent protection ahead of this conductor. Remember, I'm right here at the lugs of this transformer. So this conductor, the question you have to ask yourself is, does breaker 1 meet the requirements of overcurrent protection ahead of conductor 2? I mean, it's an overcurrent protective device. That's a given, right? But is it overcurrent protection that exceeds the value permitted for similar conductors that are protected as described elsewhere in 240.4? Well, let's take a look at 240. Let's go to Article 240. 240. I like to start the morning with 240. 240. 240 is titled Overcurrent Protection. Where's dot 4? 240.4, protection of conductors. Conductors other than flexible cords, flexible cables, and fixture wires shall be protected against overcurrent in accordance with their ampacities specified. Now, so that tells you conductor 2 has to be protected at its ampacity. Specified in 310.14 unless otherwise permitted or required in 240.4 A through H. So we have to go through A through H. A is power loss hazard, B is overcurrent devices rated 800 amps or less. And remember 240.4B, the 800 amps or less, the next higher standard overcurrent device rating is permitted to be used provided all of the following conditions are met. The conductors are being protected, are not part of a branch circuit supplying more than one receptacle. The ampacity of the conductors does not correspond with the standard ampere rating of a fuse, and the next higher standard ampere rating does not exceed 800 amps. So this is, if say for example the ampacity of my conductor is 750 amps, I'm allowed to go to 800 amps. I'm not required to go less than 750 as long as I meet the requirements in B. If the overcurrent device is an adjustable trip device installed, blah, 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 blah. Okay, so that doesn't necessarily help us right now. C is overcurrent devices rated over 800 amps, and then D is small conductors. These are all of your small conductors. E is tap conductors. So tap conductors shall be permitted to be protected against overcurrents in accordance with the following. 210.19 C and D, household ranges. This is not a household range. 240.5b2, fixture wires. Location and circuit is 240.21. We're going to go check 240.21. Reduction in ampacity and size of a busway, feeder, and branch circuits, and then you got single motors. So we could say, based upon the definition, and so far, I would argue that that secondary conductor on this transformer does meet the definition of a tap conductor. A conductor other than a service conductor that has overcurrent protection. There is overcurrent protection. Breaker 1 is overcurrent protection ahead of the point of supply. I can't argue against that because it doesn't say anything about being on the secondary of a transformer or what is between that conductor and that upstream overcurrent protective device. So far, I think it's a tap conductor. All right, so 240.4, let's go back to 240.4. Where is it at? There we go. F is transformer secondary conductors. All right, so now I know 240.4F, so I will say 240.4F. Right? So that's one reference, is 240.4F for that transformer secondary. It says single phase and multi-phase transformer secondary conductors shall not be considered to be protected by the primary overcurrent protective device. Single phase other than 2-wire. This is not a 2-wire. Other than delta-delta. This is not delta-delta. So conductor 2 is not protected by circuit breaker 1. We agree? I gotta look at the chats. Yes, Michael, hit that like button. See definition of a feeder. Let's go to a feeder. Let's go back to feeder. Where is feeder? That's in F's, Michael. Feeder. All circuit conductors between the service equipment, the source of the separately derived system. Ooh, is this a separately derived system? That's another good question. Or other power supply source and the final branch circuit overcurrent device. So separately derived system. So the question is this a separately derived system? And I will argue, let's look at the definition of a separately derived system. Separately derived system. An electrical power supply output other than a service having no direct connections to circuit conductors of any other electrical source other than those established by grounding and bonding. So we've got a delta. So we know this is a separately derived source. We know conductor 2 is a feeder. We know conductor 2 is not protected by circuit breaker 1. What else do we know? All right. Okay, so it's a set. Thank you for that, Michael. Hey, Jody Wages, happy New Year, buddy. Excellent. And then David Lang, aren't the secondary conductors part of a separately derived system? Yes, David. Yes, they are. They are a separately derived system. So, and we meet the definition of a separately derived system. Okay. We know it's a feeder, and we know it is technically a tap. Technically, I meet the definition of a tap. So I meet the definition of a tap conductor. I meet the definition of a feeder. I meet the definition of a separately derived system. Because of that delta. Us old guys call the secondary conductors taps because 240.21c was not added until the 1999 code. The 10-foot rule was 240 and applied to both feeder taps and transformer conductors. Okay, you know what, Dawn, though, I would say you old guys are accurate. They are a tap conductor because it meets the definition. If you look at the definition of a tap. Now, is there a definition for a feeder tap? Let's go back to the definition of a tap. A conductor other than a service conductor that has overcurrent protection ahead of its point of supply that exceeds the value permitted for similar conductors that are protected as described elsewhere in 240.4. All right, so let's go to feeder. Is there a feeder assembly? There's no feeder taps. No. Prior to the 99 code, there was no 25-foot rule for secondary conductors. Eric Hammond, Happy New Year, buddy. Hope you're doing well. All right, so let's do this. Now, okay, so before we go any further, we need to know our equations. So we know we know our parameters. We know we have a 30 kVA transformer, 480 or 208. We know we got the impedance. Now we have to know our equations. So full load amps. We need to determine full load amps. I'm going to do this the long way and then we're going to shorten it. So here's how I operate. We know it's a three-phase transformer. So we know we have kVA, three-phase. We have to get that to a single phase kVA. So we divide that by 3. That gives my single phase kVA. Now, I need kV at the bottom, right? So if I multiply that times 1 over kV, three-phase. The kVs cross out, I know I get amps, right? So if that would be there, and I know I would get amps. But now, that's three-phase. To make that single phase, I need to divide this by the square root of 3, so that means that square root of 3 goes into the numerator. So I'm going to take and put that square root of 3 up there. That way I can get rid of the division. All right, so now kVA divided by, this would be the single phase kVA divided by, now kV. All right, so that should work. So now square root of 3, I'm just going to say this, square root of 3 divided by 3 is equal to 1 over the square root of 3. So I'm going to get rid of this, make that 1, and make that the square root. All right, so that is how we derived this. So we have kVA, three-phase, divided by the square root of 3, and divide that by kV. Right? All right. So what's my kVA three-phase? I said it was 30 kVA. Divide that by the square root of 3, and we'll do the full load amps primary. My kilovolt on the primary is 480 volts. I have to divide that by 1,000 to get kilovolts. So that's 0.480. Right. Where is my calculator? I need my calculator. Jody, where's my calculator? There it is. So I have 30 kVA. Divide that by the square root of 3. Divide that by 0.48. It is 36.1 amps. 36.1. 36.1 amps. So, do this. 36.1 amps, right? So this is what we're going to do, Jody. Copy. Paste. There we go. And we're going to erase some things here. Let's get rid of all of this stuff. This all served its purpose. All served its purpose. All right. All right, so we know that the full load amps on the primary is 36.1. 36.1 amps. Now we need full load amps on the secondary. So full load amps on the secondary, FLA secondary is 30 kVA. Divide that by the square root of 3. Divide that by 0.208. 208 voltage line to line. Hey, Osvaldo, happy New Year. Does YY change things? Fred, YY does not change. What I'm doing here doesn't matter. Delta Y, YY, from a math perspective, nothing matters because I'm using phase-to-phase voltages, right? So that's a very good question. YY, Y ground, delta delta does not matter whatsoever because I'm using phase-to-phase voltages. 208 volts is phase-to-phase, 30 kVA, square root of 3, let's do the math. 30 kVA, 30, 3 square root, divide, 0.208 divide, 83.3. So 83.3 amps is the secondary full load amps. 83.3 amps. All right. So I got the math out of the way. Get rid of breaker 1. And I got to connect this. Whoops. I got to connect this like that. There we go. How do you like my drawings? You guys, is my artistic values fine, Eric, Mr. Hammond? All right, so I got 408 to 208. I have full load amps, 36.1 amps on the primary, 83.3 amps on the secondary. And I'll just draw delta Y ground. It doesn't matter. All these equations in this calculation does not matter whether or not it's delta, delta, delta Y ground, Y, Y. Now, what would matter is, remember, well, when we get to does the primary breaker provide protection, or could the primary breaker provide protection of the secondary conductor and the secondary panel board? Hey, Lou Petrucci, good, Happy New Year, buddy. Thanks, Eric. Thank you very much, sir. So the delta delta would get us into possibly the primary breaker or fuse providing protection for the secondary conductor and panel board. All right, so we've done the math. Okay, now we're going to make another assumption. Where's my assumptions? I'm going to have some assumptions. Let's write down our assumptions. We got to maintain our assumptions. One is this is an indoor installation. We need to know this for a specific reason, and I'll show you why as we move forward. We know it's an indoor installation. The transformer supplies a panel board. Okay, that's our second assumption. The secondary of the transformer is going to supply a panel board. And that's an important distinction as well, because that'll point us into the right articles. What else? I will, and we know the parameters, right? We know it's a 30 kVA, 480, 208, 120. We know it's delta Y ground. What else? We're going to assume the 4% impedance. We're going to assume 4% impedance. What other assumptions? Trying to think of other assumptions. All right, so I think I feel good. You're hungry. You're hungry. You're supposed to be eating and watching. Take that ham and cheese sandwich. Ooh, how about a grilled ham and cheese sandwich? Melt that cheese over the ham. Bobby Joe makes. She would take this. I'll tell you what. A little offshoot here. So what Bobby Joe would do after a holidays, I would take the ham. I would slice it up. I would grind some of it up with some mayonnaise and relish, and I would make ham salad, right? That's really good with crackers and stuff. And then we would take, and she would slice up some ham and take Swiss cheese or provolone cheese too, good. First you take the Vienna style bread and you toast it with butter. Toast it in the pan. Put butter in a cast iron skillet, brown both sides of that. Then you put your ham separate, melt the cheese on it. Bada bing, bada boom, it is delish. So hopefully you're even more hungry than you were about 5 seconds ago. So we're going to make our list of assumptions as we go up through here. Now, I know my primary full load amps. I know my secondary full load amps. Now, I need I short circuit. Now this will be an infinite bus calculation. Now remember, from our per unit theory, which you may or may not be aware of, we will take full load amps, divide that by the percent impedance, multiply that by 100 because we got to take the percent impedance and put it into per unit, which you probably are going, what the heck is per unit? Well, per unit is you take percent, divide that by 100 because the percent is in the denominator, the 100 goes in the numerator. So full load amps over the percent impedance multiplied by 100 gets me my infinite. Now, to get the maximum, this percent impedance, I have to take 90% of that. So what I'm going to do for I short circuit maximum, we'll call it infinite bus. I'm going to take, so we'll call this ISC is equal to full load amps of the secondary times 100 and divide that by 0.9 times the percent Z. Now, the 90%, the reason we do that, what they mark, whenever they mark a transformer, whenever you mark, you see the percent impedance on the transformer, the transformer manufacturer is given a tolerance of around, for this size transformer, it would be plus or minus 10%. So to get the worst case scenario for the secondary available fault current of this transformer, we make some assumptions. We assume infinite bus. If you use that FC squared, the Busman FC squared app, which is a free download, very common one, very popular device. There's some assumptions you're going to make, right? The assumptions are 0.9%, because we want, the Busman app wants to make sure you don't have a problem with available fault current at the secondary of that transformer, so things are going to be inflated a little bit or deflated. The impedance is going to be at 0.9, which times the percent impedance, so you're at 90%, because the impedance can be plus or minus 10% of what's marked on the transformer. And if 4% is marked on a transformer, then it could be 90% of 4%. So to get the maximum available fault current, you're going to use 0.9 times percent Z. So full load amps, we set on the secondary secondary is 83.3 amps. So we're going to say 83.3 amps times 100. And we're going to divide that by 0.9 times 4%. And that, so, geez, I can't remember anything, right? So 83.3 times 100, divide that by 0.9, and then divide that by 4%, 2,314 amps. 2,314 amps. 2,314 amps. So I come back up to here, 2,314 amps. So what I know is that regardless of the breaker, so there is a default value. If I go to 240, if I go to 240, 240, location, article 240, circuit breakers. Circuit breaker is part 5? No. 5 and 6 are fuses. Circuit breakers. There it is. Part 7 is circuit breakers. And what I'm looking for is, oh, maybe it's in the general requirements. Let's look in the general requirements of Article 240. There's a minimum interrupting rating. There's a minimum interrupting rating for conductors, for overcurrent devices. And I just want to get the reference for us here. What's the reference? I can't find it. Interrupting ratings. 240.16. So 240.16. Oh, let's do this. Code references. Code references. So we had Article 100. Definitions. I'm not going to get to those. So 240.16. Branch circuit overcurrent protected devices shall have an interrupting rating not less than 5,000 amps. So minimum interrupting rating. So we know, and I'm going to put down here, we said this is a panel board. We know that no matter what overcurrent protective device I have, the minimum interrupting rating is going to be fine. I don't have to worry about what is the interrupting rating on the secondary of this transformer because the minimum is 5,000 amps. Capiche? So, my overcurrent protective device, whether it's a first circuit breaker or a fuse, I feel good. Now the equipment, could the equipment have a lower interrupting rating? It sure could, because it depends on what I put in that piece of equipment. Whether it be a panel board, panel board, or say an industrial control panel, I could have an SCCR that's less. Depends on what I'm supplying. But so suffice it to say that I am at 2,314 amps. So I have everything I need to do all of my calculations. Now, first, so protection of transformer. So I'm going to do this. Article 450. Article 450 is the protection of the transformer. Article 215 and 240 is protection of the feeder. Right? We know it's not a service, so 230 doesn't apply. We know it's not a branch circuit, so 210 doesn't apply. But 215 does for feeder protection. 240 applies because for overcurrent protection. And then Article 408. I hope I got it right. 408. I always mix up 408 and 406. I believe 406 is your wiring devices. 408 is panel boards and switchboards. Yes. So this would be the protection of the panel board. In my opinion, it's really important that you separate your goals and objectives here, because we're going to pick the primary overcurrent protective device and the secondary overcurrent protective device, and you have to understand what are those devices are intended to protect. So the first step, I'm just going to give you in my journey, my opinion. Remember, everything I say here is my opinion. Could I be wrong? Absolutely. I could be wrong. That's why I need you and I need the chats, which I got to look at the chats. Does YY, Happy New Year. Your sketches are great, so no other chats. All right, so go back to the normally scheduled program. So I'm going to go to 450 and I'm going to pick my overcurrent protective devices based upon 450.3b. So I'm going to do table 450.3b. And this will be, because, why? Maximum rating we're setting overcurrent protective device. And I'm going to do my max ratings of OCPDs. Transformer 1,000 volts and less. Okay, so the next question is, do I need primary and secondary protection? Now, to answer that, we already said that because it's a delta Y ground, my primary overcurrent protective device does not provide protection for my secondary conductors. Where did we find that at? We found that, and because I'm going to write this down, I'm going to take a little note to remind you, in case you didn't know, and tell myself, I want to protect this conductor. 240.4F, another code, 240.4F, tells me secondary conductors not protected. Right? So 240.4F tells me my secondary conductors are not protected by the primary overcurrent protective device because it's not a 2-wire and it's not delta-delta, 3-wire. Capiche? All right? So there's another code reference for you, 240.4F. So I know I am going to be picking primary and secondary overcurrent protective devices. I can't use primary only. And I'm at currents of 9 amperes or more for I'm going to pick primary protection. Primary protection. If I do that, and then I do this. So primary protection. I'm using 450.3b, currents of 9, column 1, row 2, and that would be 250% is my multiplier. That's my maximum. And it says, note 3, a transformer equipped with coordinated thermal overload protection by the manufacturer and arranged to interrupt the primary current shall be permitted to have primary overcurrent protection rated or set at a current value that is not more than 6 times the rated current. Transformers having not more than 6% impedance, blah, blah, blah. Doesn't apply. Doesn't apply to me. Doesn't apply. So what was my primary protection? My primary full load amps was 36.1 at 250%. 36.1, 36.1, 2.5 times 90 and a quarter. 90.25 amps. So my maximum now if I look at the table for primary current protection, I cannot go to the next higher size because note 1 says where 125% of this current does not correspond to a standard rating of a fuse or non-adjustable circuit breaker, a higher rating that does not exceed the next higher standard rating shall be permitted. Okay, now I don't have that. Now let's go back over to 240.4F. No, I want to go to 215. Let's go to feeder protection. I want to look at feeder protection. 215. Where's my feeder protection? Let's see if there's anything in 215.3 says feeders shall be protected against overcurrents in accordance with part 1 of Article 240. So 215.3. Wait. This is primary overcurrent protected device. So I'm at 250%. So this is a feeder. And that breaker 1 is protecting that feeder. So 215.3 tells me I need to protect that feeder according with part 1 of Article 240. Part 1 of Article 240, which is your general requirements. And this is what's going to tell me that conductors other than flexible cores shall be protected against overcurrent in accordance with their ampacities specified. So this would be feeder protection. So I can't go to the next higher overcurrent protected device. 90.25 is the highest I can go. So I could put a 90 amp breaker here, max. Now, what's the minimum? What would we typically do? We have to think about, is it a continuous load? Is it a non-continuous load? We'd have to do all of those types of considerations, but typically we go at about 125%. Because what am I worried? My minimum is going to be driven by a couple things. One is the inrush current of the transformer. So, and if I looked at the inrush current, so I did look at a typical inrush current. Inrush. I know it's here somewhere. Inrush. So there's my 90.3. Oh, wow, I forgot I even had these slides. Minimum. There we go. Minimum overcurrent protected device size. My inrush current. Remember, inrush is the magnetization and whatnot of the core. So that's going to have an inrush current. Now, I took a look at a 30 kVA transformer from a manufacturer. And what it said for that 30 kVA transformer, I can expect a maximum of around 262 amps of inrush current. So what can't happen is I can't trip whatever circuit breaker that I pick on the line side based upon this inrush current of 262 amps. So I went to a manufacturer's trip curve. And if you look here, 25 to 60, because I said, if I did 125%, I could put a 45 amp circuit breaker on there. My maximum is 90. But why buy a 90 when I can buy 45? Right? Okay, so I could put a 45 amp, and if I look at whether it be a single pole interruption or 2 poles in series interruption, 400 and 500 amps is the instantaneous pickup for this circuit breaker, for this manufacturer, and the inrush is 262. So I don't have to worry about even down to a 25 amp circuit breaker. I could put a 25 amp circuit breaker on this transformer as long as I don't trip it, and my instantaneous would be high enough to live through the inrush currents. Make sense? Okay, so I could put a 45 amp circuit breaker on the primary of this transformer. Now, you would want to check 2 things. What's the interrupting rating of that circuit breaker? So I need to make sure that the interrupting rating of that circuit breaker is appropriate for where it's being placed, because remember, that's going to be in an upstream panel board or a switchboard, probably a panel board, feeding a 30 kVA transformer. It's going to come up, now that whatever the fault current is up there in the system, it has to be able to interrupt that fault current. So I've got to pick the right interrupting ratings for that device. I'm going to go with a 45 amp breaker or fuse on the supply side. And then what does that mean? This conductor, that conductor has to be 45 amps worth of conductor. So I go to table 310, 310.16. It's another code reference. If I go to 310.16, and remember, I've only got 3, because it's delta, I don't have a neutral. I've got 3 conductors and an equipment grounding conductor in raceway. So 45 amps, I'm going to go with 75 degrees C column, because I'm probably tied to a circuit breaker upstream that is 75 degrees C, and I'm going to assume that the transformer lugs are 75 degrees C as well. But regardless, the weakest link gets me to 75 degrees C. I'm at 45 amps, so I would go with a number 8. I'd go with a number 8 conductor, which is 50 amps. You might say, well, Tom, you could probably go, I wouldn't go with a number 10. I would go with a number 8. All right, so number 8 on the line side of this 30 kVA transformer, 45 amps for the feeder breaker. Are we good with that? Agree, disagree? All right. Why wouldn't you use primary only protection? You determined that the primary wasn't protecting the secondary. Right. You can't use primary only protection, because if I only have a primary circuit breaker, I have no protection for the secondary conductors. If this was delta-delta, then I could have primary only protection and I would have to follow the rules in 240. But Fred, I can't. I have to. And so that's not for the transformer. Remember, 450 only applies to the transformer. I have to think about the conductors. Where do I go for the conductors? Those are tap conductors or feeder conductors. I would go to 215 for feeders. Feeder says go follow part 1. Part 1 tells me in 240.4, which is in part 1, 240.4F tells me that those conductors on the secondary are not protected by the primary. So I have to provide protection for these conductors. Now, how do I do that? Part 1 of Article 240 doesn't give me the information I need. So where do I got to go? I got to find out these are tap conductors, because I go back to the definition. So now I go to 240.21. 240.21 is location and circuit. So where can I put my... So now, Fred, here's what happens. I have to protect this conductor. I'm out of 450. I'm done with 450. because I've picked my primary and I'm going to have 125% here. But to determine whether or not I need primary only or primary and secondary, I have to provide protection of the secondary conductor. So then the question is, where can I put the overcurrent protection for that secondary conductor? I think I'm seeing, hold on, 450. Oh, okay, so 450, now remember, 450, the primary only puts me at 125%. I'm at 125%. Because I just said I'm going to go to 125%. So if I could say, well, I'm going to use 125% and I'm primary only protection. Perfect, I'm done. Go to bed, go to sleep, I'm done. But now I need to provide protection of the secondary conductor, right? How do I'm going to get rid of all this stuff. Clear pens. So now I have to protect that conductor. So Fred, let's say I used 125% for primary only protection, and I'm at 45 amp circuit breaker, I'm done. Now I have to protect that secondary conductor. Part 1 of Article 240, 215 says follow Part 1 of Article 240. Part 1 of Article 240 tells me that that conductor is not protected by device 6, that guy up there. 240.21 says location and circuit. So now I have to say, do I have to put a circuit breaker here, right there at the lugs, to protect that conductor? The location of the circuit says overcurrent shall be provided in each ungrounded circuit conductor and shall be located at the point where the conductors receive their supply, except as specified in 240.21a through h. Conductors, so at the source of supply, which would be right here, but do I have to put it right there in the transformer at those lugs, or can I put it somewhere downstream? Well, if I keep reading in 240.21, B talks about feeder taps, but this isn't a feeder tap. Tap supplying a transformer, I go to 240.21c. So 240.21c says transformer secondary conductors. That's a transformer secondary conductor, right? Whoa. That's a transformer secondary conductor. So a set of conductors feeding a single load, or each set of conductors feeding separate loads, shall be permitted to be connected to a transformer secondary without overcurrent protection at the secondary, as specified in 240.21c1 through c6. Section 240.4b shall not be permitted for transformer secondary conductors. What is 240.4b? 240.4b 240.4b is your overcurrent protected devices rated 800 amps or less. The next higher standard overcurrent device rating above the conductors shall be protected. Okay, so I have to put a conductor on the secondary, and I can't go to the next higher. All right, so let's do this. I am going to figure out what is the maximum size that I can put on the secondary. If I put a, I don't know, say a 100 amp panel board, if I put a 100 amp panel board, I would need 100 amps worth of conductor, right? What's my full load amps? Is 30, well, no, my full load amps is what, 80 some amps, right? Hold on. Full load amps on the secondary. 83.3. If I went to, I can go to 100 amps. So what's 83.3? 83.3, 1.25 times 104 amps. So I can go to 100, I'm going to go to 100 amp secondary, 100 amps worth of conductor. I'm going to have a 100 amp panel board. I'm going to have 100 amps worth of conductor. And if I go to 310.16, 310.16, 75 degrees C, I'm at a number 3 AWG, copper conductors. So I'm in the copper, I'm in the 75 degrees C column, and I'm at 100 amps for a 3 American wire gauge. Once again, we are calling the primary a feeder because it's not the last OCP, even though the secondary is a separately derived system. Right. Yes, they're still feeders. All of those are still feeders. Even if it's a separately derived system, David, all of those are still feeders. Felix, thanks for joining. Circuit conductors between the service equipment. Right. Okay, yeah. So you guys, Eric, so I presume the source of the separately derived system includes the primary. No. Source of the secondary, source, no. From an Eaton document about higher efficiency. This higher than inrush current can be 5 to 25 times the greater. Yes. So Don, you're right. You'd have to look at what the inrush current is for that transformer and then compare that to the instantaneous pickup of that upstream circuit breaker. 450.3b for protection chart. Yep, Fred. Okay, so I'm reading chart wrong. I have a tendency to think that the primary is a branch circuit, or the definition of feeder in 100 needs clarification, in my humble opinion. So we're okay. I'm not going to go down that road yet. I'm going to stick to my discussion here with picking the secondary. So I pick a 100 amp panel board. It's going to have 100. I'm going to have a 100 amp circuit breaker. I need 100 amps worth of conductor, which is a 3 American wire gauge. I know my available fault current is 2300 amps, so I don't have a problem with short circuit current rating of the panel board and the interrupting rating of the breakers. What else? Panel board. So let's go to 408. 408. Part 3 is panel boards. 408. Got to go to 408. 410, 409, 408.30. All panel boards shall have a rating not less than the minimum feeder capacity. Overcurrent protection. In addition to the requirements of 408.30, a panel board shall be protected by an overcurrent protective device having a rating not greater than that of the panel board. This overcurrent protective device shall be located within or at any point on the supply side of the panel board. So it sort of indicates that I could provide the protection by the upstream, except 408.36b supplied through a transformer. Where a panel board is supplied through a transformer, the overcurrent protection required by 408.36 shall be located on the secondary side of the transformer. So 408.36b is going to mandate, regardless of the delta, oh wait, there's an exception. A panel board supplied by a secondary side of a transformer shall be considered as protected by the overcurrent protection provided on the primary of the transformer, where that protection is in accordance with 240.21 Charlie 1. So that would tell me if it's a delta or a 2-wire, then I could use the primary overcurrent device. But because this is a delta Y ground, I can't use the primary because of 408.36b. So I would need a secondary. I would either need a main in that panel board, or I can use a main lug only, and as long as my circuit breaker is or fusible switch is on the secondary or integrated with the secondary of that transformer. So, all right, so we picked the line side, 90 amps. We picked the feeder. We picked to protect the transformer. We picked, there's nothing in the code that says I need to size the transformer to the load. So I could put, yeah, so I don't have to worry about the load so much as making sure I meet all these other requirements. I'm trying to think of what else. What else am I missing? David? Crew? Am I missing anything? No, I think. So let's get rid of a bunch of stuff here. Where did we end up? We ended up with a 100 amp breaker on the secondary, a 3-gauge wire on the secondary. We ended up with 90 amp or a 45 amp, 90 amp max, but we put a 45 amp circuit breaker up there. What was the conductor? 45 amps worth of conductor, 310. 45 amps, we put a number 8. Whoop. We put a number 8. So this is an 8 AWG copper. And that's 3. 3 single conductors. 3 single conductor, number 8s, copper, and a ground. And then we have on the secondary, just cleaning things up, we have 4 single conductor, 3-gauge copper. Why 4? Because it's a Y-grounded system. I got to carry that neutral. And we have plus our ground. Do we feel pretty good? I think we covered what we needed. I could go up to 250%. So I can't go over 90 amps, so I could put a 90 in or less. And then if I put 90 amps in, so let's say that I did 90 amps, then my primary conductor couldn't be 3 number 8s. My primary conductor would have to be a number 3. For 90 amps, I would have to have 3 single conductor, 3 AWG copper, right? So, because yeah. What do you guys think? Mr. Garcia, wouldn't the maximum allowed primary be 100 amps since 250% is 90.25, and since the feeder we can go, all right, so let's go to 450. Mr. Garcia, the reason I cannot do that, if you look at table 450.3b, currents of 9 amperes or more, where it says 250%, I have a note that says, actually, it's the maximum rating or setting of the overcurrent protection is 250%. And I don't have any notes in here that says I can go to the next higher. Right, note 1 does not. So note 1 does not apply to the 250%. I agree with you 100%. But it says maximum rating for protection of the transformer. Now, for protection of a feeder in 215, now remember, you referenced wouldn't the maximum allowed primary, since 250% of since it is a feeder, we can go to the next rating. For feeders, you can. But this is not feeder protection. You're in Article 450. This is transformer protection. So for the transformer, you can't go to the next higher. If it was if you were just looking at feeder protection, then you can go to the next higher. But since it's 90.25 amps, and since it says maximum rating or setting of overcurrent protection for the transformer, I can't go greater than 90.25 amps. I can't go to the next higher because I'm not dealing with the feeder yet. Now, if you want to say, can you get away with do you have to use a number 8? Can you use something smaller than a number 8? Now you're in the feeder protection rules. So let's go to number 8, conductors. This is number 8 conductor is 50 amps. So the question would be, can I use a number 10 at 35 amps? Now there's an asterisk for a number 10, and it says, what's that asterisk tell you? Section 240.4D, because now you're in the small conductors. So if I go to 240.4D, 240.4D, number 10, aluminum copper clad, 25 amps. So it says overcurrent devices where the small conductors, unless specifically permitted in 240.4E through G, the overcurrent protection shall not exceed, so I'd have to put a 25 amp, it can't exceed 25 amps on that conductor. A 10 American wire gauge copper is 30. I can't exceed 30 on a 10. So I can't use a number 10 because I would have to put a 30. Now, as long as the instantaneous pickup of that 30 amp circuit breaker doesn't cause a nuisance trip on inrush, then I could put a 30 amp breaker on it and put a smaller, put a number 10 on it. Right? But I can't go over a 90. Does that help? In table 4, note 1 does not apply to the 250%. That's correct, Dawn. But keep in mind, what Mr. Garcia is speaking to is feeder protection, not transformer protection. So the notes don't apply in this regard because the title of 450.3b is maximum rating. David, it seems primary only protection applies to feeders and the secondary conductors as feeders as well. Remember, David, 450 is transformer protection only. Okay? 450, you know, I had a hard time wrapping my head around this too. But 450 applies to transformer protection only. I'm not dealing with feeder protection in 450. Secondary conductors don't matter. Primary conductors don't matter. I'm only worried about protecting the transformer in 450. And this is why, this is the order that I use. I always will pick my primary and secondary overcurrent protected devices first because I might have to go to 250% for selective coordination reasons. For what Dawn pointed out, some of these high efficiency transformers have a higher inrush current. I might have to go to a larger overcurrent protected device than I want in the overload region because the instantaneous needs to go to a higher value. Okay, so once I've established my primary overcurrent protected device that meets the protection of the transformer requirements, then I pick my conductors. And we can have the debate, right? We can say, oh, all right, so I want to use a number 8. Can I use a number 10? Right? I can have that discussion about the conductor that I select, and I have to make sure that it's protected. So if I go to, for example, in this case here, if I went up to a 90 amp circuit breaker. I couldn't put anything less than 90 amps worth of conductor. I guess I could go less than 90 amps worth of conductor as long as it is the ampacity value to the next higher size based upon the rules in 215, right? But I'd have to make sure that I'm protecting that conductor with that 90 amp circuit breaker based upon feeder protection. So that's, and I ran through, anyway. This is why, here's what I like doing. Keep doing different size transformers. Pick your maximum for the line side. Pick what would be more reasonable. I mean, outside of a design criteria that you would need to meet, that you would need a larger primary overcurrent protective device for whatever reason, whether it be the inrush currents, selective coordination, or maybe it's just the fact that here's the other issue. Whatever circuit breakers you pick need to fit in the middle, in the steel box, right? So it could be that you decide, oh my, I went to this catalog, I went to the XYZ manufacturer's catalog, and I picked the most cost-effective circuit breaker that I could find that would work, and I researched the instantaneous pickup, and I've plotted the curves, but you have an existing panel board, and that breaker will not fit in that panel board. Now you're going to be, now you need to go, what is my upstream panel board that's feeding this transformer? What breakers can I fit in there? And then look at what those options are. Don't go to the circuit breakers first. All right, I went over my time. I went 1 hour and 16 minutes. I apologize. Thank you for hanging in there for, and all that you do for the electrical industry, guys and gals. Welcome to 2024. I can't believe it is 2024. And we're going to see how fast this year goes. So please, thank you. And thanks, Mr. Garcia, Don Ganier, Mr. Engelhardt, Fred B., Felix Sandoval, Eric Hammond, the electrical wizard. Be cautious that 450.3a applies to transformers over 1,000 volts. Yes, you're right. Different rules between transformer protection. Absolutely. NHZX boy. All right. So thanks, everybody. I think it's time for me to go. All right. So hopefully we got something out of our session today. Happy New Year. Happy New Year from in the UK. Excellent. We've got the UK on board. You are the man. Thank you for joining in. Still got question, Fred B. What's your question, Fred? Let me scroll down. Got it right. You are always Happy New Year. Redondo, Happy New Year. Still got question, Fred B. Well, ask your question, Fred. You're always beauty to watch, Tom. Happy New Year from Maritala in UK. Man, awesome. We are truly an international program. Lou Petrucci, Mr. Garcia. All right, Happy New Year. Stay safe, everybody. Please, thank you for what you do for the electrical industry. Thank you for what you do for electrical safety. Happy New Year. Please stay safe and by all means, stay healthy. Take care.